I just want to start with this, and this will kind of warm us up. This is the lab stuff, but most groups started with their clay blood vessels, and I saw some, common errors that I see every quarter, which is fine, but it's good because, it forces you to learn how the vessels properly form. So first of all, just to review the first three major branches that come out of the aorta on the aortic arc here. Okay. First of all, what type of vessels are those? Are those elastic, muscular, or what's the other type? What type of arteries are those right there?
They're elastic.
Those are elastic arteries because they have to absorb that big pressure pulse that comes out of the heart. So on the left side of the body here, we have what's this vessel right there? That's the left common carotid artery going up to the head, and that has its own that merges right out of the aortic arc. What's this last one here? The left subclavian. Subclavian meaning under the clavicle. So there's the clavicle right there. The left subclavian artery goes underneath it. It goes in the scapular region, and at that point, what does it become? The axillary artery. So, obviously our models aren't really drawn to scale, but you need to have the order correct, at minimum.
At what point does the subclavian become the axillary?
Well, after it goes underneath the clavicle there, I assume right when it hits here, it says here, but I'm assuming it's, this stretch right there.
Okay.
And then it goes from the scapular region, it goes down into the brachial region. So because of that, it's called the brachial artery, and then it branches into the radial and ulnar arteries. The same vessel setup is on the right side of the body. So what does that make this? The right common carotid. This is the right subclavian, right axillary, right brachial, etc., etc. Okay, the only difference here is that instead of having their own branches there off the ascending aorta, they branch out of this structure, and what's that structure called? Brachiocephalic trunk. So I need to see all three of these arteries distinctly coming out of your ascending aorta on your clay blood vessels. That's something that I look for. You might need to spend a little time making it all, proper. Most of them looked good, so.
That's better.
90% of the time it's I forgot to put this in. Then we have the descending aorta. It goes in the back of the heart. It's called the thoracic aorta. It goes through the diaphragm, and it's called the abdominal aorta. Then it branches right here when it gets to the sacrum, and it forms the common iliac artery. I'm assuming iliac refers to the ilium region of the pelvis. Then it goes outside here, outside of the pelvis, and it becomes the external iliac artery. Then it goes in the femoral region, and it's called the femoral artery. Now these branches up here, some of them are straightforward. For instance, these guys here, what are those? The renal arteries, and you can make kidneys if you want, just kind of make something that's a kidney and then have those arteries go into them. And then there's a couple other pictures that I want to look at. But the first artery you're going to have coming out of the abdominal aorta is the celiac trunk. And every time a vessel says trunk, that means that there's going to be stuff branching off of it. So if this is your abdominal aorta, and that's your celiac trunk, you're going to have things branching off that celiac trunk. But you guys need to make a distinct celiac trunk there. Okay, I need to see that trunk coming off the abdominal aorta. Then I need to see the 3 branches off of the trunk. Okay, the branches don't come off of the abdominal aorta. Then we have the superior mesenteric artery, and this is branching and branching. And where do you think this is going? To the mesentery in the abdominal cavity to feed the digestive system. Okay, so you can just make some branches like that because it branches and it spans out. So here's our celiac trunk, and there's 3 arteries that peel off of it. What's this one that's going? What's this first of all? This organ? That's the stomach. And so what's this artery that's going and feeding the stomach here? That's the left gastric artery. And if you can just indicate, somehow that it's going to a stomach, maybe you don't have room for it. That's fine. But this is the, what's this over here in the upper left quadrant? That's the spleen. So what's this artery going to it? Splenic artery. And then this big guy here, the liver. And so the 3rd branch of the celiac trunk is the common hepatic. Okay. And then here's that superior mesenteric artery, and it just goes and it feeds the mesentery, which feeds the intestines and all that kind of stuff. I haven't looked at this material, to be honest with you, since the spring quarter, but I could, give you some questions here. I guess the first question to you guys is, are these blood vessels, are they all connected to one another, or do some of them release their products, or are all the blood vessels connected in some way or another? They're all part of the same system, so they are all connected. Okay, the blood that's in them stays within that system. Do you guys have any questions that you guys want to go over here with blood vessels? You have these elastic arteries because they stretch and recoil. So the left ventricle contracts and all of these just go, expand out. So this is a diagram of that. This is the ventricle, and this is the ventricle, and this is the aorta. And here you can see the ventricle contracts, it shoots that blood out, and the aorta, because of that elasticity, is able to stretch out a little bit and absorb some of that pressure, absorb some of that energy. And then when the ventricle relaxes and the pressure decreases here, because it's rubber band-like and it has that stored energy in it, it's able to collapse on the blood. And why is that important? Why is it important that it not only be able to stretch, but, more to the point, recoil? What's that?
To help push the blood the rest of the way through.
Right, and how does it do that? What's it doing by recoiling? What if it didn't recoil? It just stayed the same size.
Pressure when you go elastic push.
Yeah, what are we doing with regards to pressure with that recoil? Constant pressure. Okay, so when it recoils, it just maintains that pressure on the blood and keeps propelling it through. And this is evident with atherosclerosis. Did you guys watch this video and were able to identify the steps that arteries get injured by? This is a completely calcified plaque with this big atherosclerotic plaque in there. What's the problem with an artery like this? There's no elasticity to it. So, okay, blood gets pumped through here with ventricular systole and it can't expand. What's the consequence of that? Why is that bad?
Can't expand?
It can't expand, but why is that bad on it's bad on the heart, it makes the heart work harder. But why is that bad on the vessel?
Has higher pressure.
It has way higher pressure. Okay, think of this, with ventricular systole, a certain amount of blood's going to go through there. And that's a lot of pressure even when it expands. But what if you can't expand that? You're shooting that same amount of blood through, and so you're really squeezing on the walls, and so you get super high blood pressure during ventricular systole. And then also, it can't recoil. So what's the problem with that? It can't keep the pressure on, so during ventricular diastole, when the ventricle is relaxed, this blood doesn't have as much pressure and it's probably just dribbling through a little bit. It doesn't have that pressure to propel it through the system, at least through this little part here. So how does this all start? I should have put like a layers. Do I have layers of the blood vessels somewhere?
Begins with a buildup of fatty deposits.
Nope. So these are the layers of the blood vessel here. And this is the inner layer. These are they're called endothelium. The epithelium that lines the blood vessels, the special name for it is endothelium. But does anybody know what type of epithelium that is, lining the blood vessels? It's the simple squamous. Flat, not a lot of friction and whatnot. So what starts atherosclerosis? What starts this whole process? Yeah.
The damage to the simple squamous.
You have damage to this endothelial lining. Okay, this endothelial lining gets damaged. And chemicals in cigarettes, hyperglycemia, all that kind of stuff can damage that endothelial lining. And then what happens? That's when the immune cells start going in, they form a foam, it takes these plaques in it, and now you have this enlargement into the artery. And that's bad on its own, but over time, it can calcify and become harder. Atherosclerosis is hardening of the arteries. So yeah, one problem with this is that, you have super big blood pressure fluctuations, and that puts a lot of pressure on the artery. What does that also make you susceptible for? If you have these big pressure fluctuations on one part of your artery that has this plaque. What's that? An aneurysm. Okay? An aneurysm is when the artery wall weakens and it bursts. You have an aneurysm in your abdominal aorta, and that usually doesn't end well. And then you have a cerebral aneurysm, and that's a problem too. So yeah, you're susceptible to an aneurysm. What else can happen here? Along your lines with a heart attack. What if this was a coronary artery here?
Rupture of the artery.
Well, you could have a rupture of the artery aneurysm. There you go. So something can come along, a little blood clot that's circulating in your system, and when it goes to the coronary artery, it can plug that off, and that causes a heart attack. Another thing that can happen is this plaque can break off, and then it rumbles down through the arteries, smaller, 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 and eventually it's going to block something as well. This is something that should kind of be intuitive here. But this is blood pressure in the systemic circulation. This is where it's highest. This is where it's lowest. And not surprisingly, where is blood pressure highest? Closest to the heart. Left ventricle contracts, shoots it out the aorta, all of that blood, ventricle contracts, blood pressure goes up, ventricle relaxes, but because of that recoil, you still have a reasonable amount of pressure. If you didn't have that recoil, the diastolic pressure would drop way down. But then what happens is the blood goes through the systemic circulation. It loses pressure. And how come it's losing pressure?
And further away from the heart.
It is further away from the heart, but what is it about that causes the pressure to go down?
Resistance from the blood vessels.
Just resistance going through the blood vessels, hitting the blood vessel walls, it slows it down, friction. So by the time you get to the arterioles, blood pressure has really gone down and you don't even see a difference between the systolic and diastolic pressures. Goes into the capillaries, but again, then it has to travel up through the venous system back to the heart. And if you're going from the foot all the way up to the heart, that's a long ways to go. And look how much blood pressure you have propelling the blood there. Hardly anything. So so we talked about this the other day, but how does this blood get back up to the heart? Where does the pressure come from? Skeletal muscle pumps. Okay, squeezing the venous blood back up. Respiratory pumps, and they have large lumens, so little resistance. This is interesting right here. Look at the vena cava. This goes back to what we were talking about the other day. They show these little pressure blips in the vena cava. I'm just guessing here, but I think it's probably right. What do you think is causing these little pressure blips in the vena cava?
Back pressure from the heart pumping.
Be more
The
specific.
atrial contractions.
When atrial contraction and the blood goes down from the atria to the ventricles, we were talking about if there were valves in between the vena cava and the atria, and I guess they're just residual valves. There's not really a true valve, and so that probably pumps some blood back into the vena cava, and you get a little pressure blip because of it. Okay. Anybody else on anything really? Well, I'll tell you what, why don't you guys just have like a study session? Let's just take like 20 minutes or so. If you guys want to take that long, then we'll do that and see if any questions come up. Did you have a question, Jordan?
I don't really know what my question is, but can you talk about the slide where it's vessel length and obesity?
Okay. So this kind of goes to the point we were just talking about the other day, or just talking about just now.